Welcome to the video lecture of comparative design. This video discusses the topic evaluation of attribute part 1. This topic is from module 4. Let us have a quick look into the syllabus of module 4. Module 4 deals with two topics: syntax directed translation and type checking. Syntax directed translation includes syntax directed definition, and the below topics of syntax directed translation includes or covers the evaluation of attribute. This video focuses on bottom-up evaluation of S attributed definition, L attributed definition, and top-down translation. The main objective of this presentation is to learn how to implement translators for syntax-directed definition for evaluating the value of attribute. That means if we are given a syntax-directed definition, we have to build translators for them so as to evaluate the values of the attributes. Coming to the first topic, bottom-up evaluation of S attributed definition. From the topic name itself, it deals with evaluation of S attributed definition. S attributed definition is already dealt in a previous video posted. It is one type of syntax-directed definition which contain only synthesized attribute. Synthesized attribute means the attributes which gets value from the children nodes. So for evaluating the S attributed definition which contains synthesized attribute, bottom-up evaluation is required. Bottom-up evaluation means actually bottom-up parsing. So in case of bottom-up parsing, the construction of parse tree start from the leaf and move towards the root. Or in other way, we can say that in parsing, during bottom-up parsing, especially the parse tree builds in a post-order manner. Post-order means left, right, then root. Here, in case of evaluation of S attributed definition, using this bottom-up parser, the stack has been modified a little, that we can see in the next slide. So this slide explains how the stack can be modified so as to evaluate the value of S attributed definition. Here, the stack is divided into two parts: the state part and the value part. The stack, as we have learned in shift reduce parser, the stack has the capability of storing grammar symbol. In the case of bottom-up parsing, it uses shift reduce parsing technique. We have already explained in that module that the stack always handle grammar symbol. When the stack is having the handle on the stack top, we will reduce it. So the same stack we are explaining here also, but the stack here we have explained is have two parts: state stack and value stack. Value stack is used for holding the value of attribute, whereas state stack can hold grammar symbol. But while we consider LR parser, which is a bottom-up parser, which is also a shift reduce parser, it contains states. So in this particular stack, if it is an LR parser, it can contain state as well as grammar symbol. And the top of the stack can be pointed using a pointer. So in the case of reduction, what will happen, that is this slide explains. Whenever a reduction A gives alpha is made, that means if we have a production like this A gives alpha, if the stack top is having a handle like alpha, we have to reduce it to A. So if in that case, the attribute for A is computed from the attributes of alpha, which is actually on the stack top. So the attributes for A is computed from alpha means it is a synthesized attribute. It is A is a parent node which is getting its attribute from the children alpha. So a translator for this S attributed definition, which is having synthesized attribute, can be implemented by using an LR parser with a value part on its stack. So this slide explains how we can store the grammar symbol as well as value on the stack. Here we are considering the production A gives X, Y, Z. X, Y, Z is the production's right hand side, and small letter a is the attribute of the leftmost non-terminal capital A. So that is capital A is having a small letter a as the attribute, and it is getting an value for the attribute from its children node xyz by applying a function f over it. So here f of x comma x dot x comma y dot y comma z dot x is defined as a semantic rule which can be used to compute the value for the attribute small letter a, which is actually a synthesized attribute. So how we will evaluate the capital A's attribute small letter a using the stack is explained here. So when we have xyz on the stack top, it is a handle, we have to reduce it to a. So that is the thing, it is shown here. Now the stack top is having x, that means the right hand side of capital A is z, then y and x. So now stack top is having a z. We are actually pushing it on the right hand side, that is x, y, z. So z is on the stack top. Now on seeing this x, y, z, it is a handle, we have to reduce it. Reduce it means we have to pop the stack and push the left hand side of the production, that is capital A, onto the stack. So after popping z, y and x, the stack becomes empty. So onto the empty stack you push capital A onto the stack along with that attribute value a dot a. So now the stack top is having capital A. Capital A is in the place of capital X now. So here it is clear that the stack can hold both grammar symbol as well as the attribute values. Another case is that if a symbol has no attribute, then that entry is undefined. That means if this particular y has no attribute, it should be left as blank. Then the reduction makes the top decremented by 2 and the state covering A is put in val of top. That is what happened on reducing xyz to capital A. Another one is the example of a desk calculator that we have already discussed in the presentation of syntax error definition. Hope you remember this syntax error definition of desktop calculator, which can evaluate the expression followed by a enter key. This N stands for enter. L gives En, N stands for enter key. Then these are the syntax error definition corresponding to each of the production, which explains how the values for the attribute, here the attribute itself is defined as val, so how it can be computed, that is this SDD. So here we are trying to explain how we can evaluate the value of the attribute. For evaluating the value of the attribute, how we can build the translators. So next we can see the code fragment corresponding to the syntax error definition so as to evaluate the value of attribute. So these are the code fragment corresponding to each production, that is corresponding to each SDD, print val of top. Then E gives E plus T means val of n top is equal to val of top minus 2 plus val of top. How this code fragment has been written, that we can examine. That is on reduction, whenever a reduction happens, the right hand side of the production will be on the stack top. So here in the case of right hand side of the production, it will be E will be on top minus 2, in top minus 1 it will be plus, on the top it will be T. So after reducing this symbol, we have to push capital E. So that is actually written here, n top is equal to top minus r plus 1. That means n top, how we can compute that n top, that is n top equal to top minus r plus 1. That r stands for number of symbols in the RHS. So currently what is the stack top? From that we have to reduce that number of symbols on the right hand side. So if 3 is the 3, we have to pop. Then we have to push the left hand side capital E onto the stack, top of the stack. That is what it is explained. In this case also, T star F, it contains 3 symbol on the right hand side. So we have to pop the 3 symbol and we have to push the left hand side symbol T onto the stack. That is why this is actually in the top position. This is top -1. Star is in the top -1 value. Then capital T is on the top -2 position. So after removing this, we have to, that means after popping this, we have to push capital T onto the stack. But in this case also, F key is open parenthesis E close parenthesis, val of n top is equal to, this is actually top, close parenthesis in the top, then top -1, the E stands on the top -1, then the open bracket, that is top -2. So that will be popped up and this F will be pushed onto the stack. Then in this case, it is kept as blank because only thing is when it is popped off, this one is pushed on. One symbol is popped up, one symbol is pushed down. Then so the previous slide shows the code fragment. That means how to build a code fragment out of std, which will actually help us to evaluate the value of the attribute. So here it is explained based on a LR parser stack. Since it is an LR parser, it is actually building canonical LR0 collection of items. So we know that on considering the previous grammar, L gives En, E gives E plus, T gives T, T gives T star, T gives F, F gives open bracket A close bracket, F gives digit. This closures has to be formed by using the rules for computing canonical LR collection for that grammar. So here we can see that from the I0 till I13, that means 13 states are here. So based on that previous slide, we can build the SLR parsing table, and using that parsing table we can parse particular string. That is, here we are considering the string 5 plus 3 star 4n. So this is the expression followed by the new line n. So we are expecting the result 3 star 4 is 12, 12 plus 5 17. So how we will evaluate the val attribute for this particular string using the LR parser stack that is shown here. Initially the stack will be having the state 0, but corresponding to that value stack will be empty because corresponding to state there will be no value. Only corresponding for the attribute the value will be stored. Then here 0 under 5, while we examine the parsing table, we can see it will be S6. So here d.lexval, that is 5, is stored into val stack because 0 under S6 means shift. So we have to shift the 5 onto the stack as well as this 6 onto the stack. So in this case we have mentioned as d because in the previous thing F gives digit. F gives digit means it is same as F gives D. So here instead of digit it is totally written as D, digit D. So here also instead of 5 they will be representing as D. So that 5 is pushed onto the stack, then this 6, that is from the S6 it is pushing onto the stack. So this is S6, it is pushed onto this stack. So this D corresponds to this 5. So now the value corresponding to the grammar symbol D, because in the previous slide F gives digit, what we have to compute, the value is digit.lexval. So that will be computed onto this stack. Then now the stack pub is having 6 and input is having plus. So 600 plus, while we observe the parsing table, we can say that it is a production F gives D. So that will be that means the right hand side of the production is 1. The rule is 2 times the symbol is to be popped from the stack. So D and 6 will be popped from the stack. Then the F will be pushed down to the stack. Then 0 under F, you have to observe the go to part of the parsing table. Then we may be seeing a 4 there. So we have pushed that 4 onto the stack. Then now the stacked up value part of the stacked up is still having the 5 because the val attribute corresponds to the F gives digit only. That is what it is seen, F dot val. Then similarly, if we look into the next step, now the stack top is having 4. It is having the plus, input is having the plus. So 400 plus, it may be T gives F. So again, right hand side is having only one symbol. So 2 times one symbol means 2 things are to be popped from the stack. 4 and F will be popped. And T will be, this left hand side will be pushed onto the stack. And 0 under T, if you observe the go to part, it may be 3. So we will push 3. Then also now the stack is not having any value. So that T dot val is equal to F dot val. So no operation is to be performed, just copying the whatever in the value of val attribute of F, that is copied to T. So no change of stack top is required because the stack top should hold the same value even though if we reduce with the T gives F. So this plus 5 is again having the again on the stack top. 5 should remain on the stack top. Then coming to this 3 under plus. So it may be E gives T, again a reduction. So here also the right hand side contain only one symbol. So you pop the 2 times that symbol, that is T and 3 should be popped off and E should be pushed onto the stack. Then 0 under E, you observe go to part of the parsing table. You may be seeing a 2 there. Then also that is E gives T. E gives T means here the stack top is still not require any change because in the case of E gives T, that value is simply copied onto the stack, a val attribute of E. So the stack top requires no change. So it is not shown here. Still the stack top is maintaining 5. Then 2 under plus. Now the stack is having 2 and input pointer is pointing to plus. 2 under plus, it may be S8. That means shift 8. So you will push the plus onto the stack as well as this 8 onto the stack. Then, so now now you have already pushed that plus is pushed onto the stack. That plus, even though it's a grammar symbol, it does not have any value. So if it is not having any value, it should be shown as an empty entry. That is why this hyphen is put over here corresponding to this plus. In the case of states, there will not be any value corresponding to state. 0, 2 and 8 are all state. Only the grammar symbols are capital E and plus. So capital E, the value corresponding to capital E is 5 and the value of the attribute corresponding to plus is hyphen. That means no value corresponding to plus. Then, now you observe the stack top 8. 3. 8 under 3, it may be S6 in the parsing table. So we will be shifting the 3 onto the stack as well as the 6 onto the stack. So instead of 3, it is shown as D, digit. So the value of digit is the value of the attribute, that is 3 is pushed onto the stack, value part of the stack. That means whenever we push the grammar symbol, its corresponding attribute value is to be stored on the stack. That is why the 3 is stored on the stack. Then next, the 6 is a state number, so there is no value corresponding to the state. Then 6 under star, again there is a production, FDSD. So here also right hand side contain only one symbol. The 2 times it is to be popped. So D and 6 will be popped off and F will be pushed. Then 8 interrupt, it may be 4. In the go to part of the parsing table, it may be 4, given as 4. Then here also 4 as a state, the no need of updating the value part of the stack. Then look into 4 under star, it is again a production T keys F. Then T keys F means that is 2 symbols are to be popped from the stack 4 and F. Then you have to push T onto the stack 8 under T, it may be 11 in the go to part of the parsing table. So T keys F also the same value it will be storing, because in the case of T keys F also we can see that T dot val is actually getting the value from F dot val. It is just copying, no need of stack operation. Then so next is 11 under star. 11 under star, it will be S6. So in the case of S6, you have to push the star onto the stack as well as S9, that is you have to push star as well as 9 onto the stack. Star, in corresponding to star, this hyphen is shown because there is no attribute value corresponding to the star. Then after the 9, 9 is currently the start of 9 under 4. We have to observe the parsing table. In mind, you have to, or else you can draw a parsing table for this and observe this actions and go to part. 9 under 4, it might be a 6. So you will be shifting the 4 as well as 6. 4 means instead of 4 you will be writing it as D, and the corresponding value part will be updated with the 4. Then this 6 is the state corresponding to that. Then again 6 under N, it might be F gives D. So this F gives D means again digit. So you have to pop the 2 symbol D and 6. Then you have to push F onto the stack. Then 9 under F, it is 12. Then still the stack top is having the 4 because it is F gives D, just copied the digital value. Then this 12 under N, it is T gives T star. Here the right hand side is having 3 symbol. You pop the 3 into 2, 6 symbol from the stack. That is 12, F, 9 star, 11 and 8. Then you have to push 8 onto the stack, and 8 under T will be 11 in go to part. Again observe, but in that case it is to be observed that T dot val is equal to, you are reduced using the production T gives T star. Rule corresponding to that is T dot val equal to T1 dot val star F dot val. That means whatever be the value, that is to be multiplied. So the same thing, that is corresponding to T dot val, T and F dot val, what are the values, we have to multiply that. So how that will be made known to the stack, that is why it is written over here, val of top minus 2 star, val of top, that will be copied. So val of top minus 2, now it is having the 4, then top minus 1, top minus 2 is 3, 3 star 4 is 12. So now 12 will be copied. Again you observe 11 enter N. 11 enter N, the production is E gives E plus T. There also the SDD stands for that production multiplies. It is not multiplies, that is a mistake here. It is plus E1 dot val plus T dot val. So that will be computed. That means the stack top, it is to be val of n top is equal to val of top minus 2 plus val of top. Whatever in the top, that is to be added with the top minus 2. So 5 plus 12, 17 will be pushed onto the stack. Then 2 under 2 under n, it may be h7. So we will shift 17 onto the stack, n onto the stack as well as this 7. A slight mistake, instead of r is actually return. So instead of r, here we have used n till this. So here also it should be n. 2n 7. Then 7 under dollar. While we observe this, L gives E R. So both R and N are same because R stands for return, N stands for enter. L gives ER. That is L gives EN. It should be L gives EN. Then to pop the 4 symbols from the stack, 7, R, 2 and E. Instead of R, you can either use it as N or R. Then you have to push L onto the stack, then 0 under L, the go to part will be 1, then $100 it is accept. So this is how the stack part for LR parser for evaluating synthesized attribute will look like. The stack val part can store the value of the attribute. So in this case, the stack has shown the grammar symbol as well as the state symbol. Only the corresponding to the grammar symbol there will be values. In the next example, this is the example shown in your textbook. Here they are trying to evaluate 3 star 5 plus 4n, that is 3 star 5 is 15, 15 plus 4 19. Here this is the SDD, this is the code fragment for the stack using the stack evaluation for computing the value of attributes, synthesized attribute val. So on bottom up parsing, this parse tree will be considered. Also if you are using a stack that is having the value part also, it will be computing the value part of attribute 2, value of attribute 2. So on building up this parse tree, along with this parse tree, the val attribute will get filled. So this 3 star 5 plus 4n will be explained. It can be explained similar to the previous slide. This is left you for practicing. Then here one thing, here it is in the state stack, it has avoided all the state symbol, just it has shown only the grammar symbol for simplicity. Next topic is L attribute definition. L attribute definition means when the translation takes place during parsing, order of evaluation is linked to the order in which nodes are created. That means the value of attributes will be computed based on the order in which the nodes are created, while we are performing translation during the parsing step itself. Either in both top down or bottom up, the natural order for constructing the parse tree is depth first order, so that the attributes also will get computed. Here in the case of L attribute definition also, the attributes will get evaluated in depth first order. Then what is this depth first evaluation? If we are given a parse tree, this is the algorithm, the procedure that we are entering the node. Suppose this is the node n, then suppose there is some child for the node, there is a child for the node m and node n, the child is m. From the left to right can begin the evaluation of the inherent attributes of the child node m. You can start from the left node, which is the this is the leftmost child of n. Then you can proceed towards the right childs. Then you can again, if it has got subchilds, then you can repeat this procedure. After evaluating all the child, again come to the root node, then it can evaluate the synthesized attribute. Synthesized attribute means it is getting the value from its children node. Inherited attribute means it is getting either from its parent node or from its siblings. That is why I started with the root node, gone to the child, then gone through all these siblings. Here, in the case of synthesized attribute, all the nodes will be computing its value for its attribute from the children node. So this same thing, while we use a translation scheme during parsing, we can use depth-first traversal. Similar thing can be used for computing values for L attributed definition also. Then still L attributed definition means what? That is yet to be seen. So this slide explains L attributed definition. L attributed definition means it is also a syntax related definition. Only particularity is that it can inherit either from the parent or from its left siblings. So here it is explained like this. Suppose A gives x1, x2, etc. xn are the production. The attributes of the symbols x1, x2, etc. xj minus 1. They are the leftmost symbols of xj. If we are considering one of the child xj, that till xj minus 1, it is coming as the left child of the left siblings of the xj. So this xj can inherit from either xj, that is the left siblings, or it can inherit from the capital A. So the major thing is that L attributed definition can get the value from its parent node or from its left sibling. That means no value can be computed from its right siblings. Coming to this S attributed definition, we can say that all S attributed definition is L attributed because these type of restrictions apply only to inherited attribute. So this L attribute definition is very important for examination also. L is for left as attribute information appears to flow from left to right. Usually we are computing the parse tree, computing the values while parsing. We will be following the post order traversal. Post order from left, then right, then root. So when the parsing contains nodes which is having the inherited attributes, then in that case this L attributed definition is a good option. Inherited attributes in L attributed definition can be computed by a pre-ordered traversal of the parse tree. That means pre-order means root, left, right. So inherited attribute means it can attribute either from its parent or from its left sibling. So pre-order means left, the root, left, right. So from parent, from left sibling. This is an example of non-L attributed syntax related definition. So while we write the explanation for L attributed definition, you can also provide this example to support the definition of L attributed syntax related definition. So suppose these are the production. A gives LM, A gives QR. The corresponding semantic rules has been written corresponding to each production. A gives LM. This L is an inherited attribute. It is inheriting from its parent node, capital A. L dot n is equal to I, capital I of A dot I. Capital I is a function. Dot I, small letter I, is an inherited attribute of capital A. It is contributing to this, the attribute value of capital A is I, that is given to the child capital L. Similarly for M, it is getting its attribute value from L. L is having a synthesized attribute L dot S by applying a function M over L dot S. Then A is having a synthesized attribute dot S is equal to A dot S equal to F of M dot S. That is computing a function F over the M and getting its value. But A is a synthesized attribute. All synthesized attributes is having no restriction. But in the case of L attributes, restriction applied to inherited attribute. It says that it can inherit only from its parent or from its left sibling. Is that fact true in this case of A gives LM that we can examine? So L is getting the value from A, M is getting the value from left sibling. So it is okay. This production A gives LM, and its semantic rule says that this is an example of L attribute definition. But coming to A gives QR, capital QR, that R is a child node. It is getting its attribute from its parent A, but Q is a child node. It is getting its attribute from its right sibling capital R. And A is a synthesized attribute. It is computing its value from its child node Q. Can you tell that this is a L attribute definition? Of course no, because this R is the right sibling of capital Q. So Q is computing its value for its attribute from the right sibling. That is not permitted in L attribute definition. So this production and the semantic rule is not an example of L attribute definition. The same thing is explained in this slide. The reason why the previous productions are L attributed or not L attributed. Then coming to the next topic, that is top-down translation. All these syntax directed definitions are semantic rules corresponding to production. Syntax definition can be described using the attributes. So for evaluation of the values of this attribute, we have to use translations. So translation scheme. So we have already discussed in the presentation of syntax definition that there are two notations for associating semantic rule with production. First one is syntax definition, another one is translation scheme. So here we are going to discuss about the second type of notation for associating semantic rule with production, which is called as translation scheme. A translation scheme is a context-free grammar in which attributes are associated with the grammar symbol. Here also the grammar symbol is there, attributes are there, and semantic actions enclosed between braces are inserted within the right side of the associated production. Here the semantic actions will be inserted within braces. That is the particularity. It can be after the right hand side or it can be in between the symbols or the right hand side. So, but it should be enclosed between the braces. That is called as translation scheme. Translation scheme with the synthesized attribute only. If the translation scheme is having the synthesized attribute only, how we will mention that translation scheme? That here it says that semantic action can be given at the end of the right side of the associated production if it is having only synthesized attribute. This is the example for that. Here E is E1 plus T. The semantic rule is E dot val equal to E1 dot val plus T dot val. This is actually an example of syntax error definition. Its corresponding translation scheme will be that semantic rule will be enclosed within braces, and this is called as the translation scheme. Here E1 is having the val attribute and E is having the val attribute, T is having the val attribute. All the val attributes are synthesized. It is computing from its children node. So since this production contains only synthesized attribute, here the semantic actions are enclosed to the right hand side of the that means after all the symbols of the right hand side are over, we can enclose the semantic action within the braces. Next is an important translation scheme that can map the infix expression to postfix expression. a translation scheme to map infix expression with addition and subtraction to corresponding postfix expression. Capital E gives tr, R gives add of t, print add of dot lexeme, that is the semantic action, which is the translation scheme, then R1 or epsilon. Actually, the production is R gives add of t R1. But between this t and R1, the semantic action is enclosed, which is called as the translation scheme. Then t gives num, print num dot val. Here it is enclosed after the symbol on the right hand side. So main aim is to map infix expression to postfix. So if you are given an infix expression, how we can compute a postfix corresponding to this expression with the help of this grammar that we are going to examine. First we draw a parse tree for 9 minus 5 plus 2 using the above grammar. That is E is tr, R gives add of t, t gives num. So we have drawn the parse tree 9 minus 5 plus 2. So how will you come? So on traversing this parse tree, how to compute the postfix expression? For that semantic actions has been written. So here we have also enclosed that semantic action corresponding to its place in the parse tree also. Next we can see how this depth-first order traversal can obtain the result postfix expression 9, 5 minus 2 plus corresponding to the given infix expression. That is, you perform a depth-first traversal. Depth-first means come to this node, then root node, come to this node, then move towards the leftmost child, that is 9. Then its rightmost child is 9, print 9. So the 9 will get printed. This semantic rule will get evaluated here. So 9 will be printed. Then you move towards the this node's leftmost child, that is minus. So this lexeme, this lexical list will be inputting this operator. This is a lexeme minus. Then you move to this child, capital T. T's leftmost child is 5. So this is also again the lexicon analyzer is applying this 5 value, and that will be copied to this next branch, that is print 5. That rule gets evaluated. So that is what it is mentioned here. E gives tr. There is no rule. In the case of E gives tr, R gives minus tr. So the rule is add of t, print that operator, then R1. Similar thing we can see here. So this 5 will be printed out. Then this t, after the t, add of t, this rule is there. I have to print the operator. That minus will be printed. Then you go to the next child, its leftmost part, that is the plus. Then that is the lexeme, will be provided by the lexical analyzer. Then move to the leftmost child, 2, that is again will be provided by the lexical analyzer. Then the rule corresponding to is 2. Then you move upwards and move to the next child. That is print plus. That is actually a semantic rule that will be evaluated. And after that, move to this one. So there is no rule corresponding to this. So what we have obtained as output is 9, 5 minus, then 2, then plus. So this is another productions with the semantic rules, which has got both inherited and synthesized attribute. This explains the peculiarity of the inherited attribute. Inherited attribute for a symbol on RHS of the production must be computed in an action before that symbol, because inherited means it will inherit from its parent or from its left sibling. So it is to be evaluated in a particular order. Otherwise, it will be of no use. Consider this case. S gives A1, A2. The semantic rule is A1 dot in equal to 1, A2 dot in equal to 2. Both of them are inherited attribute. A gives A, print A dot in. So if we are supplying the rules for this parse tree, it will look like this. This is A1 A, then after so we have drawn the parse tree for AA. So S gives A1, A2, A1 is expanded to A, A2 is expanded to A. Then after that A gives A, where the rule is print A dot n. Then after this row A gives A, so this is to distinguish between both A's. Again the rule A2 dot in. Then A1 dot in, A2 dot in. That is the order in which we can provide the rules in the parse tree. But while we perform the depth-first order traversal, you can see that we can move to the leftmost child A and move towards the next part, that is the rule part. While we start printing A1 dot in, there is nothing to print in A1 dot in. A1 dot in has no value. It is not initialized any value. In the case of A2 dot in also there is no value. Here it is assigning the value, but here no value is for it. So this rule is wrong. So how can we correct this rule? We can correct this rule if we are inserting this rule before this A1 dot in and A2 dot in, before this small letter A is getting it reduced. So that should be supplied in prior to S gives A1 A2, that is in the leftmost part. So what are the conclusions for this? If we are using inherited attribute in translation scheme, you have to keep track of these three things. That is, an inherited attribute of a symbol on the right side of the production must be computed in a semantic action before that symbol. So here in the previous slide, it is not computed previously, even though it is an inherited attribute. That is why the mistake came. A semantic action must not refer to a synthesized attribute of a symbol to the right of that semantic action. If after the right, a semantic action must not refer to a synthesized attribute of a symbol to the right of that semantic action. If particular semantic action is there, it is referring to the right symbol. Again, it's rightmost symbol, then no use, since it is not evaluated. A synthesized attribute for the non-terminal on the left can be computed from all attribute its references have been computed. So if it is a synthesized attribute, we usually put the semantic rules at the end because it is getting its attribute from its children. So after going through all the child, it will be getting the attributes. With the L attributed syntax definition, it is always possible to construct a corresponding translation scheme which satisfies these three conditions. So if SDD is a L attributed definition, we can build a corresponding translation scheme which can satisfy all these three conditions so that we will arrive at the correct answer. But it may not be possible for general syntax data translation. That means if the translation scheme is having some attributes getting its value from its right sibling, it may not be possible to satisfy all these three conditions. So anyway, if we have both synthesized and inherited attribute, it is better to follow L attributed definition so that we can get the correct answer. So that means all the inherited attribute and synthesized attribute will get evaluated correctly. Next topic is top-down translation. Here the top-down translation means top-down using the top-down parsing. Top-down parsing, the category of top-down parser is predictive parser. Here we are using predictive parser to implement L attributed definition. L means it applies a restriction to inherited attribute. Inherited attribute means it is coming from its parent and its left sibling. So since the top-down parser always build the parse tree in pre-order form, pre-order means root left right. The same thing we can apply if we are using L attributed definition. Here Again, we are using some production. E is E plus T, E is E minus T, E is T, T is E within bracket, T is num. And its semantic action, that is translation scheme, is also provided with the braces. Here, the problem is that predictive parser, we know that the problem is to make the grammar ready to be passed through a top-down parser is to make it free from left recursion. We have to ensure that the grammar is left factored. These are the two important things in the case of top-down parsing. So here, while we look into the productions, we can see that both these two productions have got left recursion. This even one is just to distinguish between the left and right hand side of E. While we exclude this one, we can see that both the grammar symbols are same. That means A gives A, alpha or beta. Left hand side and right hand side is starting with the same non-terminal. So there is left recursion. So eliminate left recursion by applying the rule A gives beta, A dash gives alpha, A dash or epsilon. Here, while we apply this rule to this set of production, we will be getting this particular grammar. E gives TR. R gives plus T R1, R gives minus T R1, R gives epsilon, and the rest of the productions are as similar to the given. Let us examine. E gives E plus T. Corresponding to this E, we have the corresponding to this E, we have the corresponding to this E, we have E1. E, that is A gives A alpha. Alpha means plus T. So beta means again E gives E plus T or E gives E minus T or T. Both three of these productions are E productions. So this is A gives A alpha 1, this plus T is alpha 1, minus T is alpha 2, and this is beta. So A gives A alpha or beta should be replaced with A gives beta dash. So E gives beta means T. Here instead of A dash they are giving it as A, specifying it as R. That is why E gives TR. Then E dash gives, that is again instead of A dash they are specifying it as R. So R gives the alpha 1, that is plus T R, and again alpha 2 is minus TR, then epsilon. So here, while we construct a left recursive grammar, the semantic rules or translation scheme also change. In the previous slide, these are the translation scheme. But if we make a left recursion free grammar, that corresponding translation scheme also to be changed so that we should correctly evaluate the expression, even if we have removed the left recursion. So consider this parse tree for 9 minus 5 plus 2. Here, how will it get evaluated is that 9 minus 5 is 4 plus 2, 6. So to make use of the left recursive grammar, then construct the parse tree, then also supply the translation scheme, that rules, associate the semantic rules along with this parse tree, and we start computing that 9 minus 5 plus 2. So here T gives num, the rule will be that correspondingly T gives T dot val is equal to num dot lex val. So val will be computed 9. Then coming to this right, that means the previous one, that is E gives T gives num, then T gives R. Just we can observe that. Then again, sorry, T gives so it will be copied to E gives TR. So coming to this, you can see that R dot I is equal to T dot val. That is why that T dot val. That means this 9 will be copied to Ri. Then moving to this node, then this node, again the reduction, val equal to 5. Again R gives minus TR, the value. A semantic rule corresponding to that will be evaluating R equal to R minus T. R dot I minus T dot val. That is What is r dot ri? That is 9. D dot val is 5. 9 minus 5, 4. Again, we will traverse this node. We will traverse this node. Then 2 is inserted. Then here arg is plus tr. Maybe might be in the previous slide the rule might be like this: r dot I equal to r dot I plus d dot val. So that will be computed 4 plus 2, that will be 6. Then we'll be moving towards that node. So in top down parsing means pre-order traversal, root, then left, right. It will be computed as such. So the final value 6 will be computed from this expression 9 minus 5 plus 2. Another example of removal of the recursion is also shown. Here we have a gives a1y and a gives x. The corresponding rules are here. Here also we can see that there is a left recursion. So we can remove the left recursion by applying the rule. Then the grammar will become a gives x r gives y, r gives epsilon. But the rules also has been changed. Next part of bottom-up evaluation of inherited attributes will be continued in the part 2 of evaluation of attribute. Thank you.